Now that we are familiar with electric charges and the forces between charges, let's look at a concept of electric field. So we can illustrate this in a certain way. Let's say we have a positive charge here and a negative charge. Then there's going to be some pattern of influence. It's going to be some vector field, right? This isn't going to be perfect, but it should be similar here. Something like so. So there's every point has these vectors, and it's the influence of those two charges in space. Now, if I want to know what happens if I put a third charge in here, if I can find an expression for this electric field at a certain point, let's say that point there in the center, then depending on the charge, I can determine my force vector. Let's put the force vector in red. So if it's a positive charge, my force is going to be going in this way. So we'll call that F positive. If it's a negative charge, my force is going to be going in the opposite direction. But as long as I know this field, I can calculate forces. It's a what-if situation. Once I know this field, what if I put the charge here? Or what if I put the charge here? Or what if I put a charge there? So it gives us an ability to do what-if situations and not having to do the same calculations over and over again. Now, when it comes to an electric field, the definition of an electric field, it's a vector, is equal to the limit as some q in space tends towards 0 of the force vector at that location divided by the charge at that location. And so our units for electric field are going to be in newtons per coulomb. That's units. And our convention is that electric field lines those are the little vectors, enter or leave conductors at perpendicular angles to the surface. And the electric field lines will enter or leave a non-conductor or insulator, or however you want to do it, say it, at any angle. And electric fields exit positive charges and enter negative charges. So if I have a positive charge and I have a negative charge, then the field lines are going to exit the positive and remember it's going to be at perpendicular angles to the surface. And in this case, I just go straight in for the positive charge perpendicular angle, and then it's going to bend. So that it comes into the negative charge at a perpendicular angle. And the same down here. Like so. And that should be perpendicular. Come perpendicular. There we go. A little bit better. Now, this charge that we put into the field doesn't have to be a point charge. So, the charge Q that we're referring to back into this equation does not need to be a point charge. It's saying basically whatever charge you put there is going to have the same effect from the field lines. It's just going to be a larger charge or a larger magnitude. And this is only valid in static conditions. Once the charges move, the electric field moves or changes. So this is the introduction to electric fields. We'll do an example of an electric field problem, and then we will look at how we can extend this to more difficult problems.